Okay, YouTube, in this video we're going to further explore transformations of parent functions. In this video specifically we're going to look at translation transformations as well as how to quickly sketch graphs of linear equations. So let's start with this. When we talk about transformations, recall that a transformation changes the size, shape, position, or orientation of a graph. In specific though, we want to look at translations. And translations, recall, is a type of transformation that shifts a graph either horizontally or vertically, but the thing is it doesn't change its size, shape, or orientation. Okay, so it won't reflect it, it won't stretch it, it won't, I guess you could say dilate it or shrink it, okay? So let's go ahead and take a look at an example of a transformation that includes a translation in which we have this function here, f of x equals x minus 2. What we want to do is graph it and its parent function and describe the transformation that we see. So here's what we're going to do. Matter of fact, I'll kind of move this out of the way here a little bit. But we're going to start by creating a table of values. Now, what you're going to see is kind of like a doubly augmented table here. I'm going to make two little columns here. But we're going to say here are our input values, our domain values. And in this section here, what I'm going to do is I'm going to put in f of x, which f of x in this case is this x minus 2. Whoops. X minus 2. And then over here we'll write g of x, and g of x is just its parent function, okay? So let's recall that this is f of x minus 2. Its parent function would be just g of x equals x. This is going to be some linear function, okay? So filling in some input values here, I think a nice battery of values would just be these right here. But let's go ahead and plug these into our function. Now f of x equaling x minus 2, if we were to find f of negative 2, okay, f of negative 2, really what we're going to get here is the output we get when we take negative 2, take away 2 more. So we're going to get negative 4. If we were to plug in now f of negative 1, f of negative 1 in this case is going to be negative 1 take away 2 more is negative 3. We have f of 0. F of 0 is 0 minus 2, which is negative 2. And I'm starting to detect a pattern here, but we have f of 1. It's going to be 1 minus 2 is negative 1. And we say f of 2. F of 2 would be 2 minus 2, which is going to be this value of 0. So what we want to do is start by graphing this here. And we notice that negative 2, negative 4 is on our graph. So I'm going to go left 2, 1, 2, 3, 4 down. Oops. I need to change this a little bit here. There we go. So we go left 2, down 4. We'll drop that on here. We have negative 1 comma negative 3 is also a solution pair. We have 0 comma negative 2, 1 comma negative 1, and then 2 comma 0. Okay. So if we were to connect these dots here, we get something here. It's a line. And I'm going to go ahead and label this out, but we'll call this f of x equals x minus 2. So now let's go through and put our output values in for our parent function. Now our parent function is this linear function g of x equals x, or whatever the input is, that's our output. So if we plug in negative 2, then g of x is just negative 2. If we plug in negative 1, we get negative 1 and 0 and 1 and 2. We'll go through and now graph these ordered pairs. If we said negative 2 comma negative 2, we'll left 2 down 2. We have negative 1 comma negative 1, left 1 down 1. We have 0 0, 1 1, and 2 2. So we see the basic graph of our parent function here, which is also a linear function, a straight line. And what we want to do with this g of x equal to x here is essentially this. Now that we've graphed both the function here, f of x in purple, and then its parent function in blue, describe the transformation. And recall that we were focusing on what type of transformation this is. It's a translation transformation. So I noticed that basically all the points that you're seeing here from the parent function, if we were to take 2 away from them, which is exactly what this says right here, take our original parent function and subtract 2 off of it, notice that all that happened were all of our y values shifted down twice. So to describe this, we would say that we have a translation transformation, and it is shifted down 2 units. Okay. So this is what a translation transformation looks like, and it often occurs when we take an original function, a parent function here, f of x, say equals x, and either add or subtract some constant k off the top of it. But for right now, I just want to be able to describe this transformation here. Moving forward, though, I do want to comment on linear functions of the form y equals mx plus b. Now, recalling from algebra classes here, we say y equals mx plus b is referred to as slope-intercept form, where we have 2 values that we pay particular attention to, but we say m is the slope. I'm also going to list this as the rise over run, okay? And then we say b This is specifically the y-intercept. When we talk about the intercept of a graph, we're discussing where this graph runs into a given axis. And in this case, we say the y-intercept. So given some line here in y equals mx plus b form, what we want to point out is the y-intercept is this point that it touches the y-axis. And one thing that is very clear is this. We say it's at the point 0, comma b. The reason why we obtain this result is because, well, if it's on the y-axis, then we have an x value of 0. And if we were to find the f value, or the function value, when x is equal to 0, what we end up with is always obtaining m times 0 plus b, which always gives us this y equals b, if and only if x is equal to 0. So it's always true that the y-intercept of a graph in slope-intercept form is equal to this b value, and that its rise over run value is this slope value here. So all I want to do before we sign off on this video is just really quickly sketch graphs of these following equations without creating a table of values and check our work using a graphing calculator. So let's start with f of x here. We notice we have 2x plus 1. So the first thing I want to do is identify the slope and the y-intercept. So our b value in this case would just be a constant here. We could prove this by finding what is our f of 0 value, and we get 2 times 0 plus 1 is just the 1. So we get 1 there, and then our slope, since it's rise over run, I'm actually going to write this as 2 over 1, and it's positive. So we know we have an increasing function here. So let's go ahead and start by putting on our y-intercept. We say it occurs at b equals 1, or 0, comma b. And using our rise over run, we go up 2 over 1. We could continuously do this, up 2 over 1, up 2 over 1, up 2 over 1. But this would be a really, really quick sketch of our function here, okay? So I did want to check this on a graphing calculator, y equals 2x plus 1. So if we have our graphing calculator, let's go ahead and do this. The first place we want to proceed to is this y equals. And once we get here, we have a list of y equals, and we'll just go ahead and type in our function here. We say 2. Now the x key is always this key right here. It says x, comma t, comma theta, comma n. We say 2x plus 1. And then the next button we're going to look for here is graph. Once we hit graph, you'll notice that we do have a y-intercept of 1 right here, and it looks roughly like the graph that we have listed here. Okay, so I can verify that. Let's take a look at this next function here. Now we have negative x plus 2. Again, this is a linear function. We can tell because its parent function here, f of x, would just be f of x equals x. We have an x to the first power here. So our slope and our y-intercept in this case, our y-intercept is 2, and our slope in this case is the coefficient or factor that we're multiplying by our x here, which in this case is negative 1. I'm going to write negative 1 over positive 1. So in this case, we're going to have a graph that is falling, and it starts at a y-intercept of 2. So we'll start at 2, and if our rise is down 1, our run is positive 1, we say down 1, right 1, down 1, right 1, down 1, right 1. And this is going to proceed to do this indefinitely. So we'll go ahead and fill this in here. We want to make sure that we label this function here, but we say g of x is negative x plus 2. Looks like in the linear family here. And we're also going to check this on our graphing calculator. So again, remember that you'll just go to your y equals here. We can clear this out, and we say negative key. Now we have to use this negative key here, x plus 2. If I hit graph, we can see that we have this graph right here. Now the very, very last function here, say h of x equals 4. This is actually a constant function because it has no x value. This is very much like the parent function f of x equals 1. Except for I noticed that would be like 1 plus 3 more. So this is going to be shifted up 3. But the point I want to probably make here is this, or exactly make here is this. We could look at this as being 0x plus 4, where in this case our slope is 0, or 0 over 1, and our y-intercept is 4. So to graph a function that looks like this, we say go up 4 and draw a dot on our y-axis, but we're going to rise 0 and run 1, which places us right next to it, and basically all these points are going to proceed straight to the right here. So this is how we get our constant function here that has transformed the original parent constant function by being translated up 3 units. But that's what we mean by a translation transformation, as well as how to quickly sketch a line. Cheers.